right, so welcome to the fifth lecture in topic 5.4. In the last discussion, we talked about the forces acting on a charge when a charge is moving in a magnetic field. Today, what we will do is we'll talk about the forces acting on a wire where the current in which the current is flowing. Okay, so if a wire is carrying a current, and if you put that wire in a magnetic field, then how much force does the wire experience, and in which direction does the force act? So that's going to be our task today, and only after that we'll talk about the forces acting between two current carrying wires. Okay, so let us start with the discussion. Let us assume that we have a length of the wire to be L, and there is a current flowing I through the wire, and the wire of length L is in between the magnetic field. Okay, so as soon as you send in the current through the wire, there are certain observations that we can make based on how much force acts on the wire. Okay, so the first observation could be simply that force is proportional to the length of the wire. So obviously the wire has to be inside the magnetic field, and the longer the wire, the more force it experiences. So that's the first observation here. And also the force depends on the magnetic field of the the force also depends on the magnetic field, and also lastly the force depends on the current flowing through the wire. Okay, now the point is, if you change the current, like the higher the current, the more the force it feels, provided other quantities like magnetic field, length remains constant. Okay, so these are the observations that we can make if we perform this experiment. So from this experiment, if we want to include all of these variables that depends on the force, then we can simply write our formula as force equals to VIL sine theta. Now, sine theta is basically the angle between the length of the direction of the current and the magnetic field. Okay, so theta is basically here. Theta is the angle between the current and the magnetic field. Okay. Now let us ask a simple question, which is, when is the theta 0 in this case here? So theta will be 0. Let me just erase this one so that we can redraw here. So theta will be 0 when the length of the wire, or the directions of the current and the length of the wire, is parallel to the, if we put our wire like this, then we can say that at that particular situation, the angle will be 0. Okay, so when the wire is in alignment with the field, we say that the angle is 0. Okay, because the angle that we are talking about is the angle between the magnetic field and the current. Okay, and the direction of the current. So that's checked. Now the second one is, when is the angle 90 degree then? So 90 degree is pretty simple. So you just choose any plane and then you just put it in between the magnetic field in such a way that the angle between the direction of the current and the magnetic field is 90 degrees. So in this case, the angle will be 90 degrees. Check. And at what angle then is the force maximum? Now, according to the formula that we just wrote down, force is proportional to sine theta as well. Okay. So if we have theta as 0, then the sine theta, which is sine 0, will also be 0. So if sine 0 is 0, then the force will also be 0. But whereas if we have theta as 90 degree, then sine of 90 will be 1. So which is to say that force will be equal to just BI. So to answer at what angle is the force maximum, it is 90 degree. Okay, because in all the other angles, the value of a sine function will be less than 1. So that's why we can conclude that at 90 degree, the force experienced by the wire is maximum. Now, if you want to find in which direction the force acts on the wire, we can again take the help of Fleming's left-hand rule. Okay, in this Fleming's left-hand rule, it's still the same. Okay, the only difference here is that the middle finger now represents the directions of the current. Okay, conventional current. So in conventional current, what we assume is that the positive charges flow in the circuit. Okay, it's the positive charge that flows in the circuit. Now, in this example here, as shown in the diagram, let us try to understand in which direction the force will act on the wire. So we take our left hand, and firstly, the direction of the field is from north to south. So I'll have to point it like that, right? So north to south is like that, from left to right. And the direction of the current. So in this case, I have drawn the direction of the current into the page. So I do it into the page. And so I have a force direction, or in this case, the thumb is pointing downwards. So the direction of the force is down. Okay, so this is how we find the direction of the force when a current carrying wire is put in the magnetic field. So just to recall, if we have a wire in which the current is flowing and it is put in the magnetic field, it will experience some force. Okay, and the force is basically given by F equals to BIL sine theta. Theta is the angle between the current's direction and the magnetic field direction. Okay, it's an angle between the magnetic field and the direction of the current. L is the length of the wire, and the length of the wire has to strictly be in between the field. I is the current and B is the magnetic flux density. And this is for the magnitude. So if you want to find the magnitude, you use this formula. If you want to find the direction of the force, so second point is direction of the force. So if you want to find the direction of the force, you use Fleming's left-hand rule. Okay. So direction of the force is given by Fleming's left-hand rule. Left-hand rule, where thumb represents the direction of the force, the index finger represents the direction of the field, the direction of the field is always from north to south. So you always have to point from north to south. So if it's from north to south, you'll have to point your finger towards the south. So that's the direction of the field. And middle finger is the direction of the conventional current. So conventional current basically means that in a circuit, we choose the positive charge as a flow in the wire. Okay. So we'll do that much for today. And in the next lecture, we finally talk about the forces acting between the two current carrying wires. Okay, let's do that much for today.